Exam on Thursday in here. It's going to cover chapter 20 on organic chemistry. And by the way, where do we find chapter 20? Online, right, not in your book. And then it'll be chapter 11, which was on liquids, solids, intermolecular forces. And then it looks like in chapter 12 today, we will get up through section 12.5. So we'll include everything in section 12 up to 12.5. Now, mastering chemistry is not due before Thursday, except for probably a practice problem set. If you're going to skip mastering chemistry and not do any of them until it's due next week, you're probably going to be a hurting unit in here on Thursday when it comes to those solution calculation type problems. So I would very, very, very highly recommend that you do some solution calculation type problems like we'll be doing here in class today. So otherwise you don't do them, you wait till the due date on the homework quiz, then you're going to probably choke on some of that stuff here on your exam. Now the exam itself is not yet written, but what I would say here to give you some guidelines, and because it's been 7 years since I've taught this class, my recollection of what exactly goes on this first exam isn't all quite there, but typically when I do write exams, at this level of course, it will have a mixture of multiple choice problems and essay questions. Typically, if there's multiple choice on the exam, which there will be, it probably would be about 3 to 4 points per question, and probably somewhere around 8 to maybe 12 questions of multiple choice. So somewhere around 30 to 50% of the exam would be points that come from multiple choice type questions. Then I would say somewhere between about 40 to 60% would be problems of some type, and then probably like a remaining 5 to 10%, whatever that is, some sort of essay question. So at this level, I do expect that you can verbalize what types of things that you've seen and read and explain some of the chemistry behind it. Yes?
When you say an essay question, are you talking about a full essay or more of a short answer?
Essay question meaning you have to write in sentences. It's not going to be a book, but it could be 1 paragraph, 2 paragraphs, 3 paragraphs, whatever it is. I typically don't have a full page for an essay question, but usually like 1 to 2 paragraphs would be what you'd expect to see. Chapter 20, which was on organic chemistry, I did pass out in here a worksheet. That worksheet is something we didn't collect, something we didn't go over. But if you're looking for some guidance as to what types of things to expect as far as questions go, that would be a really, really good one to look over. And that would not encompass everything that you would see for organic chemistry on the exam, but it would encompass probably a pretty good chunk of what you would expect in terms of nomenclature and structure drawing and reactions. So I know your text, the chapter there went into a lot more depth. We, for example, didn't have time to cover aromatic compounds. Aromatic compounds, as much as I would have liked to have done it, will not be on this particular test. As far as reactions go, very simple reactions like oxidation and reduction of organic compounds. We looked at some couple of really simple addition type reactions of alkenes and such, but it's not going to be super complex on the reactions. You of course should know how to classify your compounds as alcohols or aldehydes, ketones, whatever they are. You should be able to write out names for those types of compounds. You should know some of the general formulas. Say, for example, in alkanes, CnH2n plus 2. Of course, I never ask you that question, what is the general formula? Rather, it would be like if you see something like a C12H24. Would that be an alkane, alkene, alkyne, or so forth? So you should have some idea then when you look at a chemical formula what type of hydrocarbon it could be. So that takes care of organic chemistry. Does anybody have any questions on the organic piece? Okay, chapter 11 was on liquids and solids and intermolecular forces. This stuff here, we looked at different types of phases and phase changes. We looked at phase diagrams and then had some terminology associated with phase diagrams. We looked at intermolecular forces such as dispersion forces, dipole forces, hydrogen bonding. So you should be able to identify which types of intermolecular forces different substances may have. In addition, predict such things as what effect it might have on boiling points and things like that, boiling points, melting points, and so forth. We probably did one or two calculations. Of course, you were assigned a few more on such things as the heat of fusion and heat of vaporization. You should know the energetics of phase changes, whether they're endothermic or exothermic, and be able to do some simple calculations with those. We looked very specifically at the heating curve of water and some special characteristics that water has that makes water a unique compound. And then wrapping up chapter 11, we looked at things like crystal structures. We did some unit cell calculations and so forth. We said, well, in order to calculate one of these items, we need to know the other four. So there's really 5 sets of different types of things you need to know, but in order to calculate the 5th one, you need to know the other 4. Yes, sir.
I had 2 questions. One, are we supposed to know the Clausius Clapeyron?
If that is needed, then it would be provided in the. I always provide a list of equations and list of constants. So I would not waste a lot of brain cells memorizing formulas. And like even myself, I need to look up. I was working with Sean a little bit here today. So what was that edge length in terms of the radius again? So L is equal to 2 times square root of 2r. So something like that. I try to put in a table to have available. Now, I still expect that you know your periodic table. Okay, if you didn't learn your elements the first semester, I would be doing a crash course in that right now. I'm never going to provide you the names of the elements because those are something that we go through too quickly, too fast, and so forth. So if you never learned your elements, the ones you should be learning are on your periodic table highlighted in gray. What else on that? Molar masses, yeah. So whatever the periodic table was that I gave you on day 1 in your periodic table, or in your syllabus, on the one side it had the periodic table, on the flip side it had the conversions. What you'll notice conspicuously absent on that periodic table, though, in conversions, is there's no metric to metric conversions. So I do expect that you know your millis and nanos and picos and kilos and stuff like that. Yes, sir.
And there's a couple of questions on chapter 11 about like changing temperature, like you drop like an ice cube in it. And
Yes.
You guys know like the thermodynamics and all that too.
Yeah, that's a first semester topic. So I assume that anything learned first semester is taken into second semester. Now, of course, that could involve some equations that we went through then, and if those equations are needed, those equations will be provided. Now, I don't provide equations for stoichiometry because stoichiometry and dimensional analysis are things that I would assume that you know already. But anything that you might look at the end of a chapter, I think your textbook does it. I forget how it lists it. It might call them key equations. Let's just look at a real quick example. Make sure I'm not lying to you. Yeah, so something like I see on page 470, it talks about key equations. If it lists a key equation, it'd be there. Now, of course, like the energetics one where you drop the ice cube in, again, that's a semester 1 topic, but if you look back to chapter 6 where that was covered in your text, then you'll see that there's some key equations listed in chapter 6. Okay? Yes?
What if we misspell one of the elements?
I would say that if it's a sound blank, you get partial credit. If it's not a sound blank, then it's no credit. So, yeah, spelling does count here because if we talk about things like this. These all differ from each other by one letter. And so spelling, I mean, I know this is probably not the example you're talking about, but they all differ from each other by one letter, and each one of them conveys a very different meaning about the composition. So unfortunately, spelling often does count. If it's a sounds like, you'll get some partial credit. If it's, like for example, I'll have students might say something like for bromine, I'll call it bromium. Well, are you talking about bromine or are you talking about barium? I don't know. So that would be one that would be like a 0 credit type spelling. Okay, anybody else?
If we have any questions with electronegativities, will it be given to us?
Here's what I'd say about electronegativities. Again, the electronegativity is started as a first semester topic. We used it some to talk about intermolecular forces in here. If you need specific electronegativity values, they will be provided for you. However, you should know your trends and electronegativities that you worked with in the first semester. When I talk about trends, for example, as a general rule, as you go across from left to right in the periodic table, what happens to electronegativities? They go up. As you go down within a group, the values will decrease. So if it's something where exact values aren't needed, but you know the trends, that's all right. But if it's something where exact values are needed, they will be provided for you. Anybody else? So things that are emphasized, what it boils down to is your problem-solving techniques. If you do waste brain cells memorizing things, it would be things like the periodic table, things that we use a whole lot of. And it should have been an expectation in your first semester course, and it wasn't, I'm sorry. But it is in my first semester course, and to my knowledge, all of my colleagues here, and it is an expectation with the second semester course here as well. Same with nomenclature. I'm not going to tell you that the nitrate ion is NO3 with a negative charge. If you see a name like sodium nitrate, you darn well better be able to write a formula for sodium nitrate. And if you don't know that, I'd be reviewing your polyatomic ions from the first semester. Okay, anybody else? All right. Well, today we are going to try to get through section 12.5, and if we look into ahead as to some of the things here that we have yet to cover up through section 12.5, there's a couple things that come to mind. First of all, one of the demos we did in here last week was one where we talked about lakes dissolve lakes. Lakes dissolve lakes. And I really should have thought about this more, because I thought I demonstrated this last week, and now that I sit here and think about it, I actually did not demonstrate this when we did it. So I'm going to step out for like about... So when we talk about lakes dissolve lakes, you may recall that we had these out here the other day. And one side we had some hexane, the other side we had here some water. And if I go ahead and put some of these into these test tubes now, how would we describe the polarity of hexane? Nonpolar. And how do we describe the polarity of water? Polar. Now water has a density of about 1.0 grams per milliliter, and hexane has a density of about 0.7 grams per milliliter. So where should we see the hexane and where should we see the water when we put these two together? On the top would be hexane, because its density is 0.7. Water should be on the bottom because its density is greater. It's 1. So now what I'm going to do here is I'm going to take a couple different substances, and the substances I'm going to take, I'll set this aside here, will be some Cobalt 2 chloride and some iodine, I2. So again, iodine, I2, and here I have some cobalt 2 chloride. And what I'm going to do then is I'm going to put these into these test tubes, and I'm going to shake them up. I guess that'll fit there and there. Great. Then we'll shake them up, and then we're going to see what happens. So looking at the formulas and the structures of these substances, what do you think is going to happen to the iodine? We'll put the iodine in the one, we'll do it this way. Iodine is going to be on your left, and then we're going to put the cobalt 2 chloride in the right. What do you think is going to happen to the iodine when we put it in here? It'll dissolve where? And why in the hexane? Right. Because iodine is nonpolar and hexane is nonpolar as well. If I take the cobalt 2 chloride, and put it into the one here that's going to be on your right, how do we classify cobalt 2 chloride first of all? Is it ionic, molecular? It's ionic. So where should the cobalt 2 chloride dissolve? In the water, because water is polar. And so not only does water dissolve other polar substances, it also will dissolve ionic compounds. So now if I start shaking, remember now that this one here is the iodine, this one here is the cobalt 2 chloride. We start shaking them up, and of course, will the water and hexane mix with each other? And why not? They have different what? Polarities is where we want to think of. Yeah. So now we look at these. I like picking these out because of their colors. Notice that the iodine dissolved in which layer? The top in the hexane, and the cobalt 2 chloride into the water layer. So it is a way then that sometimes we'll separate things out, and if you get into organic chemistry, how many are planning to do organic next semester, just out of curiosity? Great. So when you get into organic next semester, one of the things you're going to do is you're going to be synthesizing a lot of different chemicals, and you're going to want to try to separate them. And many times you're going to separate them based on their polarities. And so if you want to get a nonpolar substance extracted out of an aqueous solution, we often would mix it with something like a hexane, and the hexane would wind up extracting that nonpolar substance out of the water, and we say it partitions itself into the hexane layer. So we use these types of properties all the time, and that's used industrially. Even on a massive scale, we want to produce chemicals. It's very often separated based on polarities. Yes?
So how do you remove that non-polar layer then without wasting different parts of the ore?
Remove the polar layer from here? Yep. Well, in lab, you use something called a separatory funnel.
Yes, but with the separatory funnel, you're going to inevitably have a little bit of solution left over in the starting mixture of the non-polar and polars.
There's always going to be a little bit of waste. I mean, there just always is.
And is that true even on the industrial scale?
On the industrial scale, probably even more waste, just because it's on such a massive scale. Yep. Yep. And when it comes to things like percent yields and stuff, like you calculated in your first semester, if you have an industrial process, if you're making a Viagra, for example, if you wound up on an industrial scale having like a 50% yield, you probably have a pretty good procedure going on. Yeah.
So just curious, so if you put just like water and iodine together, and then you put like the hexane in there, would the hexane like pull the iodine out of the water?
It will, yes. But part of why I didn't do that, you can actually get iodine in there, but because iodine is non-polar and water is polar, it takes a long, long, long time for the iodine to go into the water. And even then, because of the difference in polarity, not a very large amount of the iodine will actually dissolve. So, yeah.
Do you use this for like cleaning up water pollution?
Yes, yes, it is, and all sorts of things like the original. And I don't even know, it might still be used today when you decaffeinate things, when you do dry cleaning or whatever. If you send stuff in to have dry clean, you get a grease stain or something on some clothing, you want to get it clean. You're not going to wash it in water. You're not going to take a nice suit. So you take something that would be a non-polar solvent that would extract the grease and stuff out of there, and leave behind your suit or whatever it is that's going to dry out. They use much more friendly chemicals now compared to back in the day. I remember getting really ill one time. My dad had a suit dry clean and come home in a car and just broke out in hives and everything because it smelled like you were walking around with gasoline, like a suit had been soaked in gasoline. It was just so bad. But I can't say that they're entirely environmentally friendly today, but more so than they were, say, 40 years ago. Okay, anybody else? Okay, so now one of the types of forces, well, let's list first of all the forces we looked at the other day. We looked at dispersion forces that act. We talked about dipole forces. We talked about hydrogen bonding. And so these are all different ways that solute and solvent can interact with each other, is by these forces. These aren't only forces that act from the same substance to another molecule of the same substance. They can act the molecule of one substance with molecule of another. So, for example, if we had something like this stuff, which of course you need to know for Thursday, what is this stuff here? Which type of alcohol? Ethanol. And this stuff here, which is? Water. So these two are going to dissolve in each other. Of course, a lot of us do that on Friday nights, right? Or Saturday. And if you do that, part of the reason why they mix with each other is because hydrogen bonding is what causes these two to interact. You have the partially positive hydrogen of the water molecule that can interact with the oxygen atom of the ethanol molecule, or the oxygen of the water molecule with the hydrogen of the hydroxyl group in the ethanol. And it turns out one of the really cool things about ethanol is that ethanol has a mixed polarity. It has a mixed polarity because actually the one side of it here has hydrogen bonding that is available. But if you didn't see this, what does the rest of this molecule look like? Polar or nonpolar? The rest of this looks like it's nonpolar. So it turns out something like ethanol can dissolve in water, but it can also dissolve in something like gasoline, which is nonpolar. And so because of its mixed polarity, it has some rather unique characteristics. And in fact, in the winter, some of you may, and if you do this, you're doing so unnecessarily, but you might buy some heat or some isoheat. And if you buy heat or isoheat, put in that in your gas tank in the state of Minnesota, you are wasting your money. Because if you buy heat, you're buying methanol. If you buy isoheat, you're buying isopropyl alcohol. And the whole purpose of those at one point was because of what happened in the winter many times is you have your gasoline, your gas tank, and you get some condensation on form in your gas tank. When that condensation forms, solubility between, this is a whole lot like gasoline, these two will not dissolve in each other. And of course, which one is more dense between the water and the hexane? Water is. Same with gasoline. If you had gasoline and water, the one that's more dense is the water. So what happened is the water that would condense in your gas tank would go to the bottom of the gas tank because it's not soluble in the gasoline. Then it'd be in the bottom, and then it'd get drawn into the gas line. And then what would happen? Gas line would freeze up because they wouldn't mix with each other. So then what we'd do is we'd add in some heat or isoheat, and well, of course, heat is methanol, but it still has that mixed polarity type characteristic. And what would happen then is because these alcohols have the mixed polarity, this stuff would dissolve into the gasoline, and at the same time it would dissolve the frozen water droplet or whatever in the gas line, and the water then could wind up being carried through your gas tank. So today, you don't ever really hear about people, at least in Minnesota, having their gas line frozen. And the reason why you don't is because by law in Minnesota, we are required to have this stuff in our gas. And so because you have this stuff in there, ethanol in there, it will serve the same function as either the methanol, which is the heat, or the iso heat, which is the isopropyl alcohol, in that it will be able to dissolve any water that gets in there. So any water that condenses in your gas tank now will mix together with the gasoline and the ethanol that's in there, and will just get carried right on through the gas line without freezing. So if you're buying heat or iso heat still, you're wasting your money because you already have, in Minnesota, this stuff in your tank. Okay, any questions? All right, so one that's missing on here, though, is what we call ion dipole forces. And of course, ion dipole forces describes how we get this stuff here, to dissolve into water. So ion dipole forces are exactly what it sounds like. It's when ions interact with polar substances. So again, remember, dipole is another name for a polar molecule. And so the way that this works would be something like this, and there's probably a diagram here in your text that shows this. And maybe this was back in chapter 11. Let's see here if we can find a photo of this. I am looking at page 440. Page 440 in your text. And in this diagram, it's showing how ion dipole forces wind up working. There we go. And so we have water molecules. This is showing an example of sodium chloride. Water molecules will surround ions, and in this case here, the partially positive oxygens orient themselves to the positively charged ions, or if we flip the water molecules over, then the partially positive hydrogens will orient themselves to the negatively charged ions. And one of the things we'll be looking at here in this course a little bit later on, though you should still know it at this stage, where we'll be looking at it in greater detail, we might ask ourselves, why do some ionic compounds dissolve and why do some not dissolve? So let's first of all talk about why they might dissolve and why they might not dissolve. Something like sodium chloride or table salts is a very soluble ionic compound. And it's going to dissolve simply because the energy associated and the forces that act between the ions and dipoles here, that is the sodium chloride ions and the water, those forces are stronger than the forces that act between the sodium and the chloride ions together. And so as long as they can interact with each other, you'll have an ionic compound that is going to dissolve. Now, a couple things will wind up determining whether or not those ionic compounds will dissolve or not. And one of them would be like the size of the ions. The size of the ions can be a determining factor, as well as the magnitude of charge on the ions. As far as the size of the ions go, let's say we had a positive ion that was like this size here, and a negative ion of about this size. And we had another one where we had a positive ion that was about this big and a negative ion that was about this big right here. Well, which one of these two do you think would be more soluble in water, and why? The one that's more soluble is the one here on the right-hand side. Now, the reason why it is on the right, go ahead.
Is that because there's such a difference in the positive and negative?
When you talk about the difference, it's actually the space between the nuclei. If we measured the distance here from here to here and compared it to this distance is smaller versus this one here. And as an example, I brought out some magnets here, and that's kind of what's been sticking to my cart. we could kind of compare these, just think of these as being oppositely charged ions. If I start with them and they're really close together, how easy it is to pull them apart. It's a lot more difficult to pull them apart, but if they're already starting at some distance further apart from each other, it's already going to be easier to pull them apart. And so the charge on these is centered, the charge is always to the center. And again, if we start with the nuclei further apart from each other, it's already going to be easier to separate them. So typically, the larger the distance between the nuclei in the ionic compounds, the more readily an ionic compound is going to dissolve. And then the other factor here is the magnitude of charge. And what does magnitude of charge mean? Let's say we compared sodium ions and calcium ions. What can we say about the magnitude of charge between sodium and calcium ions? What does magnitude mean?
Quantity.
Quantity. It means how big something is. Okay, so we talk about different magnitude earthquakes, for example. The larger the magnitude, the stronger the earthquake. So which one between sodium and calcium has a greater magnitude of charge? Well, what is the charge in a sodium ion? Sodium. One positive. What is it on calcium? Two positive. Which one has a greater magnitude? Calcium does, exactly. And then if we compared something like nitrate and sulfate. Nitrate is NO3 with a 1 negative charge. Sulfate is SO4 with a 2 negative charge. So what do you suppose magnitude of charge would have for an effect if we compared same size? Let's say we're now dealing with same size. So these are single positive. And just to make sure that they truly are same size, I'm going to copy and paste, because then I don't have to worry about drawing. Copy and paste. There we go. And now in the second one, I have plus plus and minus minus. So single positives up here, two positives down here. Which ones are going to be more likely to dissolve? A single positive. Why? Right, they're going to be less attracted to each other. As soon as we increase that magnitude of charge, we're going to wind up increasing their attraction for each other. And so what we find out, for example, if you go back to your solubility rules from first semester, by the way, if you need them on a reaction, that's another thing. What are we going to provide? You don't need to know, you should know kind of your general solubility rules, but if you need to know your exceptions and everything, you will get a table of solubilities that show all your exceptions. But something like the phosphate ion, which has a formula PO4 with a 3 negative charge, is something that tends to be insoluble, while something like a nitrate ion, the compound has a nitrate ion, which is NO3 with a 1 negative charge, it tends to be soluble. So the magnitude of charge then is another big determiner in the solubility of different substances. Okay, any questions you have with that? All right, so next up here, we're going to go back. We're going to do calculations. I don't think we've done any calculations in here. I guess we did some heat of fusion, heat of vaporization, but we're going to get back into calculations. And when we get back into calculations here, this is going to start a string of calculations. The math that we're going to get into right now is pretty much stoichiometry, but what we'll be getting into in chapter 13 or whatever, that's when you really need to know your algebra and your like your higher level algebra. We'll be working with things like natural logs and logarithms and exponential functions and so forth. So you'll want to start brushing up on your math, because this is going to start a string of math related concepts here for about 10 weeks in here. And actually through most of the rest of the semester, but a really good hardcore math stuff coming up in this course. So we're going to start it off, though, kind of getting us back into stoichiometry. And we need to know these units. These are the units with which you should be able to work in here. They are percent by mass, percent by volume, and what we call a mass volume percentage. Percent by mass, percent by volume, and again a mass volume percentage. You need to work with molarity. I'm going to move this down a bit. Molarity. And all of these are things up to this point that I would expect that you've covered already. What's going to be new now here in this chapter are these. They are the concept of molality. We have parts per billion and parts per million. And then we're going to look at mole fraction and mole percent. So these are all units with which you should be able to work proficiently with come our exam on Thursday. So if we start as a percent by mass, these can be labeled as a percent m over m, if you wish. And of course these stand for grams of solute per 100 grams of, not solvent, solution. And these labels in the numerator and denominator are very important because some of you say solvent, and there's some of these that do have solvent in the denominator. Most of them have solution. And actually these wouldn't have to be grams. These could be any mass units. They could be kilograms over kilograms, as long as whatever the mass units in the numerator and denominator are the same. Percent by volume would be grams of solute per, not grams, but milliliters of solute per 100 milliliters of solution. And again, it wouldn't have to be milliliters. They could be any volume units, as long as the volume, they could even be quarts. They could be quarts of solute per 100 quarts of solution, as long as the units in the numerator and denominator are the same. Now the one where it does matter is in the mass volume percentage. Your masses must be in grams, and your volume must be in milliliters. So this is grams of solute per 100 milliliters of solution. And so if we say that something is 35% by volume, if there's 35% by volume, that means that there is 35 milliliters of that substance per every 100 milliliters of that solution. Isopropyl alcohol, rubbing alcohol, I don't have the original bottle here, but rubbing alcohol is 70% by volume. If it's 70% by volume, that means that there are 70 milliliters of isopropyl alcohol for every 100 milliliters of solution. Okay? Toothpaste is something that happens to be marketed like this. It's a mass volume percentage. If you have a little tube of toothpaste, you'll see it's like a 0.15% fluoride ion, and it's a mass volume percentage. Molarity, we should know molarity. We abbreviate molarity with capital M. And this is calculated by taking, not grams, moles of what? Solute. And dividing it by liters of solution. And of course, when we do it like this, that means we wind up with units of molarity, which are moles per liter as our units. And we abbreviate molarity with which letter? M, exactly, capital M. So if we have a solution with a capital M, and how do we read that if we write 1M? How do we read it? 1 molar, exactly. So 1M means we have a 1 molar solution, means that we have 1 mole per liter. Molality is abbreviated with a lowercase m. This is probably a new one, and this is defined as being moles of solute per kilogram of solvent. And again, be very careful about this one, because this is the first one now that we have solvent units in the denominator. We abbreviate it with a lowercase m, and we read that as a 1 molal solution, where this right here we'd say is a 1 molar solution. And if we have a 1 molal solution, then the units would be 1 mole per kilogram. And of course it's implied that it's per kilogram of solvent, as long as you know that definition. Okay, then we have parts per million and parts per billion. They're typically defined in terms of mass units. So if it's parts per million, this would be grams of solute per what? Per, what does the M stand for? Million. So it'd be grams of solute per 1 million grams of solution. And if it's parts per billion, like this one here, parts per billion, we would define that as being grams of solute per 1 billion grams of, I think we got that all, of solution. What types of things do we measure in parts per million and parts per billion? Things that have really, what type of concentrations? Really big or really little? Really little. So we measure things like lead in drinking water or mercury in drinking water in units of parts per million or parts per billion. And then the mole fraction, this is exactly what it sounds like. A mole fraction, first of all, is abbreviated, a Greek letter, whatever that Greek letter is, and it's defined as being the moles of solute over the moles of solution. Moles of solute over moles of solution. And the terminology we use, we don't say that something has like a 0.5 mole fraction. Well, I guess we could say that. Usually there's no units on it. What we say is that the mole fraction is 0.5. And there's no units on it because the units are moles over moles, and the units wind up canceling each other out. So usually we abbreviate it with this Greek letter, which I forget the name of it. Anybody remember? Is that chi? Yeah, I don't remember the Greek letter right offhand, but the mole fraction is represented like this. And then if we want the mole percent is found by taking the mole fraction and multiplying that by 100%. So now, with all of these definitions in place, we should then be able to calculate a number of different things. And so we're going to spend the rest of the hour doing calculations today of different types of concentrations and converting back and forth between units. And we'll start with a very simple one. Let's say that we dissolve 25.0 grams of C6H12O6 is dissolved into 125 grams of water. We'd like to know what is the percent by mass. Of this solution. What is the percent by mass? Okay, so we start with the simple ones here. Percent by mass. We start with grams of solute and divide by what? Divided by how much? 100 and what? We do not divide by 125. That's your first error. Divide by 150, exactly. Why are we dividing by 150? Because the definition is grams of solute per grams of solution. And the solution contains the solute and solvent. So it's got to be both of them. So if we calculate this, we would take the 25.0 grams of C6H12O6. We divide it by 150 grams of the solution. And once we do this, then we'd have to take this result and do what with it? By 100. Yes, and so we take 25, we divide that by 150. That's a fraction of 1/6. So 1/6 is the same as how much? I can't do this in my head. Well, I can, but you can't. You have to get the calculators out. How much? It's not going to be 1.6. 16.6, which it's 16.666, which will round up to 16.7. And it's a percent by mass, so we usually write it as m over m. I always say 16.7% by mass. And if we want to be more specific, we'd say C6H12O6. Any questions on this one? All right, anybody need a calculator? No. We're going to do some more calculators today. Anybody need one? Okay, get them out. If you need one, I need some collateral. Get them out. Okay, so next one here. Let's start with this. We'd like to know what mass of C6H12O6 would be added to 635 grams of water to make, and we're going to make 0.100 little m C6H12O6. And remember, what does little m stand for? Molality. Right. So now, since this one is molality, we need to know our formula for molality. We'll come back to the formula here, and we say that molality is equal to moles of solute per kilogram of solvent. And then we remember that 1 mol stands for 1 mole per kilogram. So now, with this one here, we're looking for mass. So the mass is, and this is going to be the mass, is this a solute or solvent? Solute. This is stuff we get dissolved. So we're going to be finding the moles of solute. Once we find the moles of solute, then we're going to take the moles of solute and convert that into grams, because we want a mass. So with this one, if we're going to calculate moles of solute, that means we need to know the molality and we need to know the kilograms of solvent. Do we know these two? Yes, we do. So let's start here with the molality. The molality is 0.100 molal, and this is C6H12O6. Now remember that little m, molality, stands for moles per kilogram. So when you do this, what I would do right away is I'd substitute that mole with the actual units, which would be moles of C6H12O6 per kilogram of solvent. And in this case, the solvent is which stuff? Water, right. And then, of course, if we're trying to solve for moles of solute, what are we going to do with the molality and the kilograms of solvent? If we want to calculate this, what do we do with these two? Multiply them together. Of course, now, this here is kilograms of solvent. We are given units of grams. So we can't deal with different mass units. We have to make them be the same unit. And we're in good shape as long as we remember that a kilogram is the same as 1,000 grams. So I'm not changing anything. What I'm doing is I'm just taking that definition and I'm putting it in the units that are more convenient. So the units I'm putting down here are moles per gram. And again, I can do that because the denominator was 1 kilogram of water, and now we just substitute with 1,000 grams of water. It's the same stuff, same amount, just in different units. So now that we have that, we can then multiply this by 635 grams of water. And what happens to our units now? They cancel out, and our units are moles of C6H12O6. What are we trying to find? Grams of what? C6H12O6. So we come back here, we put what on the bottom? Moles of C6H12O6, and on the top we put in grams of C6H12O6. And how in the world are we going to get a conversion between grams and moles? What is this called? Molar mass. So we go back to our periodic table, and I'll pull up the periodic table here. You need to pull yours out. Remember, you got that in day 1 in your syllabus. So we have 6 carbons, 12 hydrogens, and 6 oxygens. I'll go ahead and add these together. 6 times 12.01 plus 12 times 1.008 plus 6 times 16.00. And I wind up with 180.156. Of course, we don't need all those digits. Probably 180.2 would be sufficient. And what happens to our units here now? What cancels? Moles. And of course, this leaves us with units of grams of C6H12O6. So we'll take 0.1. We'll multiply that by 635. Multiply again by 180.2. Or you can put the whole thing in if you want. And we're going to divide that by 1,000. And wind up with an answer of 11.4427. How many significant figures should be in that answer? 3. So round this off to 11.4. The units would be grams of C6H12O6. You guys are new to me. You haven't seen me grade a whole lot unless you're in lab, and then I've only graded 1 lab of yours so far. But I am picky on things like significant figures and units. If you just wrote down 11.4, that's not a full credit answer. If you put 11.4427, way too many digits. If you put 11, you're not going to get full credit. I do expect that by second semester you do know your rules for rounding for significant figures and such. If you don't know those, again, go back and review. Any questions? Okay, let's calculate the mole fraction and mole percent of the solution. Calculate the mole fraction and mole percent. And the solution again is if we, let's see, calculate the mole fraction, mole percent, when 11.4 grams of C6H12O6 is dissolved in, and we'll have that be in the 635 grams of H2O. So if we want to calculate the mole percent, we need to find the moles of solute. Remember that the mole percent is the moles of solute over the moles of solution. So we need to find each one of these. So we'll start with the solute. Starting with the solute, we've got 11.4. Oh, do we have this amount somewhere? I don't think we've calculated it yet, though, have we? All right, so we have 11.4 grams of C6H12O6. And to convert this to moles, what do we need? Molar mass. So molar mass would be 180.2 grams of C6H12O6 for every 1 mole of C6H12O6. Divide that by 180.2. Should be a familiar answer. Pretty close. Yep. So it looks like we have 0.6 0.06326 moles of the C6H12O6. Slide it over a bit. I'm running out of room, so hopefully we can see all of this packed in here. That's our solute. We then take our moles of water, which we don't yet have, but we do have 635 grams of water. And what do we need to do with this? Convert it to moles. So on the bottom we'd put in grams of H2O. On the top we'd put in 1 mole of H2O. And how do we figure out the number of grams here in 1 mole? Molar mass, right. Molar mass of water is how much? 18.02. So we add those up. There's 2 hydrogens and 1 oxygen. Grams of H2O are going to cancel out. We take 635 divided by 18.02, and we wind up with 35.24. 35.24. Label on this is going to be moles of H2O. So now what do we do? How do we find the moles of solution? Right, we need to add these two together to get our moles of solution. So sum these together, and we're going to get 35.30. Of course, in terms of the uncertain digits, it's the tenths place that is uncertain, so there would be this many moles of solution. So then to find the mole fraction, I am going to have to flip over to the next one here. Flipping it on over to the next page, we take the 0.06326 And this will be moles of the C6H12O6. We divide this by the 35.30 moles of solution. And 3 sig figs in both the numerator and denominator. We go ahead and divide this out. We wind up with an answer of 0.001. And how many sig figs do we need? 3. So how many more digits do I need? 2 more. So this would be 0.00179 would be the answer. And so again, a mole fraction is exactly that. We say that the mole fraction of glucose in the solution is 0.00179. There are no units on the mole fraction. If it would, we would simply say the words mole fraction C6H12O6. Any questions on that? So the other one then was the mole percent. What do we do to get the mole percent? Times 100. So this is going to be 0.179%. I would actually say that this is mole percent of C6H12O6. Now you might be wondering why we create all these different units. There must be some purpose. It's not just to torture Gen Chem students. There is a purpose. We can mention it real quickly here, but we won't actually see it till after the exam a week from today. But it has to do with different behaviors of solutions that we call colligative properties. And like in your Chem 1 class, I know that most semesters you do a thing where you boil water in lab, and I know it's a fun lab, right? But when you boil the water, you add some salt into it, what happens to the boiling point of water? It changes. And does it increase or decrease? It increases. And it's called boiling point elevation. And it turns out that the degree to which the boiling point increases is based on the molality of the solution. Same with freezing point depression. If you add some salt to water, it winds up freezing at a lower temperature. That is also based on the molality. The colligative property of osmotic pressure depends on the molarity of the solutions, and the vapor pressure depends on its mole fraction. So again, these different things depend on different units that we use to express the values. Okay, let's do, any questions yet here? We could say mole percent, we could just put in the symbol in there as well. Is that what you're asking?
We'll just say 0.179% moles.
Usually we say mole percent when we describe, yes. Okay. Anybody else? All right, I have one listed here. I have page 513, number 27 in your text. What does 27 look like? All right, this would be a good exercise to go through. So this is a silver nitrate solution. So silver nitrate solutions are often used to plate silver onto other metals. We'd like to know what is the maximum amount of silver in grams that can be plated out of a 4.8 liters of silver nitrate solution that contains 3.4% silver by mass. And let's assume that the density of the solution is 1.01 grams per milliliter. So ultimately here at the end, this is page 513, number 27. Let's write down some of these facts here. Again, we have 4.7 liters of silver nitrate solution. I can't see this. There we go. And this silver nitrate solution contains 3.4% silver by mass. And the density of the solution is equal to 1.01 grams per milliliter. Yes?
Isn't it 4.8, not 4.7?
Is it 4.8? That's why I put my glasses on.
Sorry.
4.8, you're right. And now I can't see anything. Okay, so now if we want to calculate this, what's going to be very helpful when you work with densities is remember what the densities stand for. And it's going to stand for grams of solution per milliliter of solution. So you should always write down complete definitions of your units when you work with them, because these are typically going to be solved by dimensional analysis of some sort. So to do this one, let's start with our 4.8 liters of silver nitrate solution. Right there. And if we are going to work with our density is, again, grams of solution per milliliter of solution. That probably means that we're going to have to convert our liters first over to units of milliliters. So to convert liters over to milliliters, on the bottom we'd put in 1 liter of solution. On the top would put in for every 1,000 milliliters of solution. And of course then liters of solution are going to cancel out. Then we can take our density. We take the density. We now have 1.01 grams per milliliter. Where's the 1.01 going to go? I hear the top and I hear the bottom. It's going to go on top. So there's this many grams of solution for every 1 milliliter of solution. And the milliliters of solution cancel out. And then we're told that this solution is 3.4% silver by mass. If it's 3.4% silver by mass, this means that it contains 3.4 grams of silver for every 100 grams of solution. Exactly. So where's 3.4 going to go? Top or bottom? Why is it going to go on the bottom? Yeah, look at the units, and this is why it's important to write these out. Where's the 3.4 going to go? On the top. There's 3.4 grams of silver for every 100 grams of solution. We want our grams of solution to cancel out, and we're trying to calculate grams of silver. So now that we have that all set up, we can multiply this on through. We'll take the 4.8, multiply that by 1,000, multiply again by 1.01, multiply that by 3.4, and then we'll divide that result by 100. When we do that, we wind up with 164.8 whatever. So 164.8 grams of silver. But now we do need to take something into consideration, that is significant figures, which this answer should have how many? 2. So the last digit we want to keep here is this one. So do we round this off to 16, or what do we do? 160, but if we write it as 160, number of significant figures isn't clear, so we'd have to put this in scientific notation. Putting it in scientific notation would have 1.6 times 10 to the second grams of silver, and that would be the answer. And if we write it as 160 grams, we don't know whether this trailing zero is significant or not, so when we don't know whether it's significant or not, we put it into scientific notation to clarify the number of significant figures. Okay, and I think that kind of takes care of where we're able to get to today. I wrote down here some problems that I thought would be a good idea practicing here for your exam on Thursday from this section. I'm writing down number 31 would be a good example. Number 37. Number 39. Number 35. So I guess I skipped one here. So if you're looking to practice some more problems along the lines of what we could expect on your exam on Thursday, these would be some practice problems. It basically comes down to unit manipulation. Yes?
As far as everything that took,
Everything through section 12.5,
which is today.
which is today.
Anything we take tomorrow is not going to be exactly.
But there's no tomorrow. No, there's no tomorrow. This is the last class before the exam. So anybody else? Seating chart from A to Z in here. I will be spreading you guys out and whatever else. And there will be mostly people with elbow room, but few instances like right in here where you will be elbow to elbow. We'll see you Thursday. I will be excited to see you in my office, as would our tutors. If you need help.